Hello and welcome to this pointwise application video. Today we're going to be talking about putting a fully structured hexahedral mesh on an aneurysm. The geometry was provided as part of a CFD challenge hosted by Dr. Gabor Yaniga, and he's currently preparing the results, which will be available in early 2014. I've also provided a link to his website in the description below, and I encourage you to visit if you're interested in more information. Before we begin gridding, I'm going to introduce a little bit of terminology that we're going to be using throughout the video. First of all is the database. By database in Pointwise, we mean the imported geometry, the underlying structure that we're going to be putting a grid onto. Also, when it comes to gridding, the term dimension is going to come up a fair amount. Dimension is simply the number of points along a curve. That's going to be directly related to your final cell count and dictates the number of cells that are going to be connected to a given curve. Speaking of curves, in Pointwise we call grid curves connectors. So a connector is simply a one-dimensional grid. You can think of it that way. It can have arbitrary curvature. It doesn't have to be just a straight line. And those connectors are then going to be used in sets of 4, or a minimum of 4, to define domains, which is a two-dimensional mesh. You can see here on the right, these are connectors, just a line here with a number of points distributed along them. And then by gathering collections of these that have they're dimensionally balanced, we call it, meaning that opposing sides have equal number of grid points, you can create a 2D mesh, which we call a domain. And then lastly, we can collect these domains in groups of a minimum of 6 and form a fluid volume, in this case a cube, which we call a block. I'm also going to be talking about an elliptic solver. And if you're unfamiliar with gridding technologies, an elliptic solver is just a mathematical construct that helps you take a grid, look at the grid lines, and smooth out some of the imperfections and sudden changes in cell area or the grid line angle, etc. So, getting back to our application, this is a picture of our final topology, the final product, what we're going to be working towards today. You can see that with the tools in Pointwise, we're able to construct a very smooth, high-quality mesh, and we're going to be talking a little bit more throughout about how we gauge that quality. But one of the overall themes today is this is a very organic and very circular geometry. So using automated tools and fully automated methods to create a completely structured mesh can sometimes be problematic and difficult with any program. However, the tools in Pointwise give you the ability to really have ultimate control over your mesh and control the final grid quality. So speaking of this circular geometry, since we're dealing with structured meshes, it requires a little bit of extra topology that I'm going to try to introduce you to. If you have a perfectly rectilinear system, a structured mesh is very easy to apply. You can see for a square like this, opposing grid lines are simply connected and you have a perfectly decent mesh. However, whenever you go to a circular domain, all of a sudden you have very skewed cells near the junctions of these adjacent corners due to the curvature of the connectors at the edge of the domain. In order to eliminate these, because these highly skewed cells are going to be very problematic for your CFD solver, we introduce additional topology to the interior of the domain. By simply introducing a little more structure to the interior, we're able to regain excellent orthogonality near the walls and then smoothly transition to a nice perpendicular core of grid points in the center of the domain as well. This type of topology is often called an OH topology, after the O-shaped grid lines on the outside and the H-shaped grid lines near the core. I'm going to be using this topology a lot throughout this application, so I wanted to introduce it up front in case you were unfamiliar. We also need to define the overall topology. Since we're defining a volume mesh, we need to have some idea of where we're going to be going with the blocks as we create them. So what you can see here is a sketch of our topology that we're going to be working towards. Each of the arteries is going to have an OH structure. So you have a H core denoted by these red dashed lines, and then O blocks surrounding it. These O blocks are actually going to join the O blocks from an adjacent artery, and the H cores are actually going to feed into a common junction that will then propagate into the bulk of the aneurysm. Now, one other thing that I'm going to bring your attention to is this tip block, as I call it. Because of the very continuous and smooth transition here, it's not possible to simply take this OH topology from the junction and terminate it at the end of the aneurysm, because that would lead to a collapsed edge, essentially. So by introducing a block at the bottom of the aneurysm, we're able to terminate all of the grid lines and get a very high orthogonality structured mesh without using any poles or collapsed edges. So now that we have a general idea of where we're headed, let's go ahead and jump into Pointwise and get started. Now, Pointwise is a bottom-up meshing program, which means that we're going to start with the geometry, sketch out our general topology, create a wireframe, then move to a surface mesh, and then create our volume mesh from that. So what we see here is in Pointwise, we've already imported our geometry. This particular geometry was provided as an STL format. Pointwise fully supports discrete geometries like the STL format, but the tool set that we're going to use today is going to be a little different than if you're used to working with native CAD in Pointwise. So I'm going to be stepping through the differences and kind of highlighting how to approach this particular type of geometry, but you'll see after the first step it's really pretty much the exact same. So one thing to note whenever you import an STL format is that each of these points here on the triangulated surface mesh are pickable points in Pointwise. So for a good high quality, high density surface mesh like this particular STL, there are actually a number of points that we can snap to whenever we're sketching our initial wireframe. However, to make things a little easier, I actually found that applying database points to the surface of the mesh made it a lot easier to sketch out these curves. So you can see very faintly there are a number of points that I've already placed on the surface. In fact, if I turn off the model, you can see that that artery has already been fully sketched out here with a number of points. So that just means for us at this stage we just need to connect these dots, because we're going to use these points to define the control points for this curve that is going to define the long direction of this inlet artery. So we simply connect those points and click apply. Now, if you were doing this on your own, you could go in and connect the other connectors, and I've happened to color code these, which helps whenever you're working with this type of file a lot. But today we're actually just going to accept this, and I've already drawn the other curves. So I've hidden those in another layer I'll turn on, and just so that everything's consistent, I'm going to put this curve in layer 1 as well, just so that everything's there together. So now I'm going to go ahead and turn off those points, and you can see that we've already sketched out the general structure of this one artery. However, at this point, the wireframe is not exactly conformal with the mesh. Or with the model, I apologize. The overall structure is close. We've got the right general shape, it's in the right vicinity, and point to point it's matched, because remember that each of those control points lied on the database surface. However, the overall wireframe is not conformal to the mesh. So what we need to do is actually project it onto the underlying database. So in order to do that, we simply drag and select all of these connectors, and then we either go up to the toolbar and click project, or go to edit, project, and then we're going to use a closest point projection. We're going to project all the points, including the endpoint, so we can uncheck interior only. And then we're going to go ahead and target a database and select the surface of the aneurysm and the artery, as opposed to this inlet database surface here. We'll click end there to end the target selection, and then project. And so you can see, if we zoom in here, the yellow curve shows where this connector, where the wireframe is going to be projected onto the model. And that's exactly what we were after. We now have a nice conformal wireframe that exactly is lying directly on the surface of our aneurysm. So we can go ahead and turn the aneurysm off again. And so now the next step is to actually create our surface mesh. So we already have a nice wireframe. We just need to create our mesh. So with the curve still selected, we go up to the toolbar and click Assemble Domains. So with one click of the button, it's going to create these 6 domains, one for the inlet, one for the outlet, and then the 4 domains defining the wall. Now, just out of the box, this is not too shabby. It's a pretty decent domain, but you can see that there's a little bit of skew. In fact, we can quantify that if we go in with the examine and look at the minimum included angle. You can see that there's actually this pocket here with the minimum angle down below 50 degrees. And in fact, I'm going to go ahead and just apply a lower and upper bound of 45 to 90 degrees just so it stays consistent when we come back and look at this later. The other thing that we should point out at this point is that whenever the curves were projected onto the surface, the distribution changes here. So we actually are going to want to go ahead and reset that distribution. So we're going to select all these connectors, go up to Grid, Distribute, go over to the Functions panel, and then click on the Hyperbolic Tangent option. That's going to redistribute so we have a nice equal spacing along that outer grid line and no jumps in cell area or anything. So now returning to this surface mesh grid quality, we can go ahead and highlight all 4 of these domains. We can go up to Grid and Solve. We'll jump over to the Edge Attributes panel. We'll highlight the boundary conditions at either end. We're going to set a spacing control of a user-specified 0.1. This is going to enforce the grid spacing near these edges and make sure that as we solve the grid, it doesn't pull away from those edges. We're also going to change the angle control from orthogonal to interpolate. This is particularly handy whenever you have a grid line like this one, where you go from one acute angle to another. Rather than enforcing an orthogonal boundary condition and forcing these grid lines to come out of this edge at 90 degrees, we're going to interpolate so that we smoothly transition from this line to this angle. It gives you a smoother mesh. Otherwise, if it came out at 90 degrees, you would force these grid lines here to bunch up next to this edge. Lastly, we're going to select the longitudinal connectors, the long edges here, and we're going to change the boundary condition from fixed to floating. This is going to allow these edges to float and move around as if they were internal grid lines, and that helps them find their optimal position and can help really improve the overall quality of the grid. We're next going to go to the Attributes panel, and we're going to constrain the surface shape from free to database. This is going to require the interior points of the domains to lie on the underlying database as well, and so that'll make sure that it's nice and conformal with our artery. We're then going to go over to Solve and run this for 10 iterations. You can see that on the first step it's going to pop out, and then on subsequent steps these connectors are going to float around just a little bit. We're going to hop back over to Edge Attributes though and change these long connectors from floating to orthogonal. By doing so, we're going to actually let them be fixed in space, but we're going to allow the grid points to move along them. And we're now running for another 90 iterations to really help smooth this mesh out as much as we can. And you can see that the grid points are just kind of sliding along those curves. We then select OK, and if we now go back and go into Examine and look at the minimum included angle, you can see that this is a much better mesh already. You can see that we're almost perfectly orthogonal here the majority of the way down the artery. So the next step that we need to do is we need to introduce this OH topology I talked about before, because we have a nice, great quality mesh on the sidewalls, but these meshes here at the end really are very lacking because of this very high skew at that junction. So you can go in and manually draw this, or you can use a script, which is going to be made available on Pointwise's GitHub repository. So in the interest of time, I'm just going to run this script. So you simply go up to Script, find the name of the script. This one is Create OH. It's going to pop up a dialog and ask for the radial dimension, whether or not we want to run the solver. And in this case, 11 is going to be perfectly fine for this. We do want to run the solver. This is referring to the elliptic solver. So we're going to just select the defaults. It is then going to prompt us to select 4 connectors. So we're going to select the 4 connectors defining this outer inlet domain. And we'll click Done, and you can see that it's going to create a nice high-quality OH topology here on the end. Now we can run the same script again, going up to Script and re-execute, or the Control-E accelerator. Select the defaults here, but we're not going to run the solver on this end, which will become clear for reasons I'll explain in a little while. We then highlight the connectors, click Done, and we now have the OH topology there. Now we're almost there, but we found in working with this, because of the twists and turns of the aneurysm, or the artery, I apologize, it helps to divide this into two different sections. One, this nice straight artery section, and then the other where the artery starts to twist and turn as it enters the junction. So to do that, we're actually just going to split these domains with edit and split, and we're going to pick a point about halfway down. We're going to repeat this using the accelerator, Control Q, for the other three domains, and that will allow us to divide this problem up into two portions. One at the entrance, where the artery inlet is over here, and then where the artery enters the junction. Whenever we're running the blocks solver a little later, you can see why it would be useful to kind of isolate this region of high skew and everything from this nice uniform region at the beginning. We're then going to run the OH script one more time. We're going to accept the default settings, select these 4 connectors, and click Done. So we now have our OH topology defined, but we're still lacking some internal structure because we need to connect these points up on the interior of the OH topology. To do that, we're going to be using the copy and paste command in Pointwise. So we could draw curves manually, but because of the twists and turns, it's going to be a lot easier to just copy and paste. That way the connector already has the natural curvature that we want. It's also by default dimensionally balanced, since we're going to eventually want to balance this connector with whatever we place in between these points there. So we're going to copy with Control C, paste with Control V, and then we're going to be prompted with a number of options for transformations to apply to this pasted connector. So we're going to apply a translation. So we click this. It's going to then prompt us for an offset vector. And so we can go in and just pick points. We'll pick the endpoint here and where we want that curve to lie in after the transformation. And you can see that this yellow curve now is a great representation of, or great approximation to this interior structure that we want. It's not perfect, but we can actually fix that here in just a second. So we're going to accept that and then accept the paste. Now, as you notice, this is not quite matched up yet, but we can apply another transformation via the edit, transform, stretch command. And this command is going to take this curve that we've selected and stretch it given the parameters we provide. The first one it's going to ask for is the anchor, where we want it to stay still. So we're going to click this other endpoint that we've already matched up. The next 2 points that it's going to ask for are the endpoint and then where we want that point to lie after the transformation. So we click the end of that newly created connector and then where we want it to match up on the OH topology in the middle of the artery. You can then see with the yellow curve that that's exactly where we want it to lie, so we click OK. Now creating the remainder of the internal topology is very straightforward. It's the exact same process, so I'm going to skip over that a little bit and jump ahead to a fully created copy of this file. So the next step is we have this wireframe internally. We need to create our domains just like we created the surface domain. So we're going to go ahead and select using the inclusive selection, holding down the Shift key, and select all the connectors for this outer OH topology. We're then going to click up here on the Assemble Domains. Now you can see that some domains were created, but if you look down in the message window, only 7 got created. Pointwise errs on the side of caution whenever you give it a long list of connectors and tries to create the minimum number of domains necessary to connect that topology. And because of that, it erred on the side of caution and did not get this last domain. But with a few mouse clicks, we select those connectors, click on Assemble Domains, and you can see that it pops the last domain into place. We're going to repeat the process over here, Assemble Domains, and I'll also note that you can tell kind of from the density of grid lines where that domain got overlooked. We'll click that again, and now we have our internal structure completely defined. The next step is going to be highlighting all of this internal structure, highlighting all of these newly created domains and the surface domains, and then assembling blocks to define our fluid volume. So after selecting all the domains, we click on Assemble Blocks, and 10 blocks have been created, which is exactly what we expected. We have 4 defining the outer portion for each of these 2 segments, and then we have our inner H core. The next step that we need to do is going back to that topology I sketched out at the very beginning. We need to provide some 3-dimensionality for this junction here so that this artery can connect to the adjacent artery and the aneurysm. So in order to do that, we're going to actually select this curve and transform it and just kind of move it around to give it that 3-dimensionality we wanted. So to do so, we go up to Edit, Transform, translate. Now there's a number of ways you can define this translation. If you were in a nice aligned coordinate system, you could provide an offset vector manually by entering values in XYZ notation. But because of this organic shape and the fact that we're not aligned with a coordinate system at all, really, we're just going to pick a couple of points here on the surface of the artery itself that will kind of give us an approximation of where we roughly want this curve to lie. So that works all right. And again, this is a lot like drawing the curves on the surface initially. It needs to be in the right general vicinity, but it does not need to be in exactly the final location, because we're going to be using solvers later that will smooth things over a little bit. So we're going to apply another transformation to this other connector down here in much the same way. And we'll just kind of try to give it a little bit of three-dimensionality so that whenever we go to connect it up with the adjacent topology, it matches well. So that's going to be the procedure that you would go through if you want to manually construct the mesh using an existing script, but primarily building this by hand. So what I'm also going to do is I'm going to kind of showcase how you could do this in one step with another script that we're going to have available on the script exchange as well. So in order to use this other script, we're basically going to just highlight these connectors. We're going to create essentially an H block, one H block for the entire artery. So I'm going to use this artery here at the top, and so we're just going to select all those connectors and click on Assemble Blocks. That's just going to create a regular H grid on all of the connectors here. And after we have this block, the next thing we're going to do is we're just going to go up to Script and run Butterfly Maker. We're then going to click to select interactively, and that's going to allow us to pop back over here and select the one block that we wish to create this butterfly topology with, or this OH topology as I've been calling it. So we'll select Done. It's going to then prompt us for which direction and some other parameters here. We're actually going to make this match the other one, so we'll make that 11, a dimension of 11 on those ribs. And then we'll want it to be in the the I direction as opposed to the J or the K direction. If we want, we can preview this topology. It'll take just a second for it to run. It's basically going to be stepping through and creating all of that topology that we made in the first step. And so you can now see that we've got this nice OH topology there. We'll select OK, and that will create our OH topology. So that pretty much covers the arteries. So we've now created these internal structures, and I'm going to go ahead and jump over now to a completed set of this artery plus the other two. Now I've gone ahead and run the block solver, which I'm going to be talking about a lot later, but that's really smoothed over the grid and really made a high quality grid. So we can start looking at the volume mesh now by highlighting all of the blocks with Control A, going up to examine and looking at a metric such as the volume ratio. And this goes in and computes the ratio of adjacent cells, and you can see that our volume ratio for these arteries is less than 2, which is really not bad. If you had a higher threshold and you wanted them all to be less than 1.5, you can identify them with this examine tool, which I'll talk about more later. So that's really the artery. So we're just about there. We have really everything kind of in place now to go ahead and create this junction, and then from there we can go ahead and create the artery or the aneurysm as well. So I'm going to go ahead and hop over to the Layers tab and pull up the junction topology that I've already created. Now, I created this outer topology the exact same way as I created the aneurysm. Or the arteries, I apologize. The curves were initially just placed on the database, much in the same way as I created those curves for the artery. I then created an OH topology with that script, and then I came in and manually drew some 2-point connectors here to connect up this topology. Otherwise, it's exactly the same process. Now I've also gone ahead and worked on the surface mesh as well, and I've done a little bit of smoothing to get a good quality grid there. But all in all, it's the exact same process as we used on the artery, so I'm not going to go over that today. So the next step is we actually want to create the internal topology here. So I've grouped all those connectors that we defined in here so I can easily select them. We'll select that group and then click on Assemble Domains. We can then hide this junction surface just for a second so you can see this internal topology, and we can see this junction block has been populated, and as well as these domains that define the edges of the O block for the aneurysm. So we'll turn that surface back on. We're going to highlight all of these domains. Need to select the domain selection mask, and then we're going to click on Assemble Blocks. You can see that this created 5 blocks, which is exactly what we expected. And we now have a volume mesh defined for the upper half of the aneurysm. So all that remains is creating the internal topology for the aneurysm. So I'm going to turn on the connectors. Again, I've already run the smoother on these and projected them so they're conformal with the database. But what we need to do is define that inner topology, that tip block and everything that I was talking about at the very beginning. So to do that, we're going to turn over our selection mask to connectors. We're going to highlight this bottom topology here, which is topologically consistent with this H block up here. We're then going to go and copy and paste this selection here. And we're going to use this to create that upper portion of the tip block that I talked about earlier. By copying and pasting as opposed to drawing manually, we're able to copy the dimensions, etc., etc. And so it really kind of helps. Makes things a little easier. I'm also going to go ahead and turn on some points that I created earlier, much like I did whenever we were creating the artery topology. I just placed these points on the database surface for convenience, and whenever we're applying these transformations to this pasting operation, I'm going to use these points to define, for instance, the first operation we're going to apply is a scale operation. So I'm going to use this point to scale to represent the origin of that scale transformation. So that's essentially, it's going to scale all of the components that we've selected and are pasting, and this is the origin of that transformation so that everything scales relative to that point. We're going to input a constant scale of 0.7 in the X, Y, and Z location, and you can see that the preview scales about that central point and has provided us with a nice smaller copy of this initial topology. So we'll accept that, and then before we accept the paste, we're actually going to apply a second transformation, namely this translation, and we're going to use 2 more points on the body, as we did before with the whenever we were creating the 3D topology for the junction out of the artery, and we're going to displace this upward into the body of the aneurysm. We're then going to select OK and accept the paste. So this is going to form kind of the upper surface of that tip block that I was talking about earlier. But for reasons that'll become clear a little bit later, we're going to go ahead and actually remove the control points for these curves. The reason being, whenever we go in and create the topology to connect this, this inner H block, we don't want to have a very smooth corner here because that is going to be the corner of a cell, and you want that to be a nice right angle ideally. And so you can see that if this had the curvature that it has now, whenever we go to create that block, you're going to have a very splayed cell. So just to make things simpler, we're going to go ahead and remove those points now. So we'll go up to Edit, Curve, and then delete all interior points. We're going to repeat the process over here on the other one, Edit, Curve, delete all interior. The next step is going to be very similar to creating the inner OH topology on the artery. We're just going to select this curve, copy, paste, translate, and we're going to clear the old translation vector, specify a new one, select OK, apply a transformation, edit, transform, stretch, select our anchor, select the end of this newly created connector, and then select the topology we want to match up with. Then select OK. The other thing that we want to do before I get too far along is we want to actually complete this bottom topology down here. So I'm going to go up here and create 2-point connectors. Now we want to be careful here. The dimension of these connectors is going to need to match the dimension up here, which was 11. So I'm going to change my default dimension to 11. We'll go back to 2-point curves, and we're going to simply connect these points here, 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 and lastly here. So that defines the rest of the topology needed for that tip block and really helps us, and that'll be used here in the next step whenever we go to actually create the volume mesh. So we select OK. Now one thing I'll note here is that even though we've already removed these control points and made this more orthogonal, this curve, after we've pasted it, still comes in at a fairly shallow angle. So to improve the quality of this, I'm actually going to go in and manually tweak the way this curve intersects that plane. So we're going to go into Edit and Curve. We're going to zoom in here. I'm going to go ahead and delete some of these control points by holding down the Shift key. We're going to delete those and then delete some of these up here as well. I'm going to go ahead and manually create a couple of points, and then I'm going to move this point around by clicking and dragging. We can then move around a little bit, kind of get an idea of how this looks, and you can see that this looks much better because we now have better orthogonality with this face, and we haven't adversely affected the quality in relation to this mesh on the side. So we're going to say OK, and then again, these jagged edges we don't need to worry about too much because we are going to be running the solver on it here in a little bit, and that'll smooth that over. So I'm going to go ahead and jump into our completed geometry. And so now this has all of the internal structure, and all that's really lacking is the internal domains and everything. So I'm going to go ahead and select those. Again, I've grouped the connectors for convenience. We'll go up here, go Assemble Domains, and you can see that the topology is going to be created. So we have a nice internal structure ready to go. We'll go ahead and turn on the surface. We'll change our selection mask to include domains. We'll highlight all these domains and click on Assemble Blocks. By doing so, we create 6 blocks, which is what we expected. We have the tip block, and then the typical 5, the 4 OH, and then the central H core. So we're looking pretty good. I'm going to go ahead and turn the surface off just for visibility purposes. We'll highlight these blocks that we just created and go into Examine. So we're going to examine the minimum included angle. And you can see that out of the box with the automated creation of these domains and blocks, we wind up with a minimum angle of about 25 degrees. That might be perfectly acceptable, but I think we can do better. So we're going to go ahead and try to find out where the problem areas are and see if we can't really improve. So I'm going to aim for a minimum angle of 40 degrees because I think once you get to about 40 degrees, you know, that's a really good quality cell, and that shouldn't give your solver too much of a hassle. But that threshold can be whatever it needs to be for your particular solver. And you can see right out of the box, we have a huge problem area where we have this large group of cells that are all less than 40 degrees. In fact, we can get a number on that if we click histogram and then turn on show histogram. We can see that we actually have almost 5,300 cells that are less than 40 degrees. So that kind of tells us where the area is, and if we get out of that examine mode, we can see that this domain actually does have a lot of skew. Just because of the way the connectors were created, the domain itself has a lot of skew. And anytime you have a bad quality surface mesh, that's going to propagate into the volume and create problems in your volume mesh as well. So we're going to go ahead and use the solver, the elliptic solver, to improve the quality of this, just like we did on the surface of the artery before. So we're going to actually specify an orthogonal BC on this inner wall. Then we're going to specify on the other 3 walls a fixed boundary condition, but we're going to change the spacing control to user specified 0.05, and then the angle control to interpolate. We're going to go back over to solve and run this for 100 iterations. You can see that the grid points are going to move along here, and we get a much better quality, much higher orthogonality mesh than we had before. So we're going to select OK. If we now go in and select all the blocks, we can see that we have a much better quality already. Examine min included angle. We can see we're already down to about 1,500, almost 1,600 cells. Now there are still a good number of cells that are less than 40 degrees, so I think we can still do a little bit better. So we're going to go ahead and hop out of this and go up to Grid Solve with the blocks selected. So by selecting the blocks, we've now entered the block elliptic solver, which allows us to actually solve the entire volume simultaneously. So we're going to go over to face attributes and change the face attributes from fixed to floating. We're then going to go back to solve and run this for 5 iterations with all the other default settings. You can see as it evolves here, the yellow lines are going to show up, and these faces have kind of floated around a little bit. That's exactly what we specified and asked for, and that's what I was talking about earlier in regard to having those curves not being exactly in the right spot, because the solver will move them around and position them ideally. We're going to go ahead and select OK, go back to examine with the blocks still selected, and look at min included angle, and we can see we now have no cells less than 40 degrees. In fact, the minimum angle in the entire volume here is 41.2. So you can see that those tools can be very, very powerful and very useful. The examine tool in particular allows you to identify problem areas and really hone in on portions of your mesh that might need a little more attention. So that about sums it up. We're going to go ahead and turn on the other layers that contain the remainder of the mesh. And so what you can see now is our completed mesh. You can see that the surface mesh is very smooth with nice smooth transitions from block to block. You can see that it is fully structured. There are no poles or collapsed edges anywhere within the volume. And overall, we have very good quality. One last metric that we'll check, we'll highlight all of these blocks. We'll go back up to examine and look at the equiangle skewness. This is a measure of the total skew in the cell, and the mathematical definition can be seen here, but what we're going to do is basically use this as a estimate for how it might behave in a solver, because the skewness affects the discretization error in most solvers. A lot of solvers advise a skewness less than 0.85. You can see that for this mesh, we're actually less than 0.6. So we're well below the recommended threshold. And again, if your particular solver has more stringent requirements, you can go in, pinpoint the areas that need more attention, and use the tools in Pointwise to achieve the highest quality grid that you would like. So with that, that about wraps up the meshing. If you have any questions, I encourage you to visit our website at www.pointwise.com/support. Thank you very much.